The Second Industrial Revolution, which drove the European and North American economies since the late 18th century, had reached measurable limits in both technology and infrastructure by 1870. The First Industrial Revolution, spanning approximately 1760 to 1850, established mechanized textile production, iron-based construction, and coal-powered steam engines as the foundation of industrial economies. Factories expanded production capacities significantly, canals and early railroads facilitated trade, and urban populations grew rapidly. Census data from Britain, Germany, and the United States show that industrial cities such as Manchester, Birmingham, Pittsburgh, and New York experienced population increases of 50 to 100% in the decades following 1800. By 1870, the scale of industrial activity, urban concentration, and international trade revealed the structural constraints of early industrial technologies. Iron, which was central to the earlier industrial economy, reached its mechanical limits. Wrought iron, employed in bridges, rails, machinery frames, and ship components, lacked the tensile strength and uniformity necessary for emerging applications. Engineering surveys of railway lines in the Ruhr Valley, Pennsylvania, and northern England document frequent failures of iron rails under increasing locomotive loads, particularly as trains grew heavier and faster. Bridge inspections and municipal records indicate that wrought iron trusses often required reinforcement within a decade of construction. Reports in professional journals, such as the Proceedings of the Institution of Civil Engineers, quantify these deficiencies, highlighting that iron could not sustain the increasing demands of urban infrastructure, long-span bridges, and industrial machinery. The repeated identification of these limitations in technical literature illustrates a documented need for a stronger, more adaptable material to underpin continued industrial expansion. Energy systems faced parallel constraints. Coal-fired steam engines, which powered factories, railroads, and mills, had improved in efficiency throughout the early 19th century. However, by 1870, they had reached practical performance limits. Engine specifications in technical manuals and manufacturer records show that the most advanced beam and horizontal engines converted less than 15 to 20% of fuel energy into mechanical work, and further gains required new engine designs or entirely new energy sources. Factories, particularly in textile production, faced significant spatial and logistical limitations. Centralized power sources required extensive transmission shafts, belts, and pulleys, which constrained factory layouts. Correspondence among industrial engineers in Britain, Germany, and the United States emphasizes the operational inefficiency of scaling production within these structural constraints. Expanding a factory often necessitated the addition of multiple engines, creating complex mechanical networks prone to failure and high maintenance costs. These documented energy and mechanical bottlenecks established a clear historical limit for mid-19th century industrial methods. Machinery precision constituted an additional limiting factor. Early industrial machine tools, while revolutionary in automating spinning, weaving, and metal shaping, lacked the tolerance control needed for large-scale mechanization of complex components. Company records and workshop ledgers from metalworking firms in Sheffield, Berlin, and Pittsburgh indicate frequent rejection rates for parts due to dimensional inconsistencies exceeding the functional requirements for emerging machinery. Correspondence from engineers and metallurgists during the 1860s and 1870s consistently notes that incremental improvements to existing machine tools would not suffice to produce the mechanical accuracy demanded for new products, including locomotives, textile machinery, and manufacturing equipment. The recorded evidence of rejected parts and misaligned machines underscores the technological ceiling imposed by early industrial tools and highlights the imperative for precision engineering. Urbanization and demographic growth compounded industrial pressures. By 1870, cities that had developed around textile mills, ironworks, and coal mines were approaching spatial and infrastructural saturation. Census records and municipal planning reports show that London, Berlin, Chicago, and New York experienced unprecedented urban growth, creating demand for housing, transportation, public utilities, and municipal lighting systems. Factories required more energy and materials than ever before, while municipal authorities struggled to maintain infrastructure capable of supporting large populations. Reports from municipal boards in Paris and Manchester document the repeated failure of iron-based bridges, inadequate steam-powered pumping stations, and insufficient transport networks, confirming that industrial systems designed in the early 19th century were no longer adequate for urban-scale operations. Scientific and technical knowledge had advanced sufficiently by 1870 to enable solutions to these constraints, but the implementation of these innovations required systemic transformation. Metallurgists, chemists, and engineers had been conducting experiments in laboratories and workshops across Europe and North America for decades. German chemical firms such as BASF and Bayer were developing controlled laboratory methods for chemical synthesis, while metallurgists in Sheffield, Essen, and Pittsburgh were experimenting with higher-strength steel production techniques. Electrical engineering was progressing from experimental demonstrations to practical applications, including arc lighting, early dynamos, and electric motors. Records from professional societies and patent offices indicate that experimental breakthroughs were systematically documented, tested, and prepared for industrial adoption. Letters between engineers and industrialists reveal recognition that the limitations of iron, steam power, and low-precision machinery could only be overcome through the adoption of new materials, energy systems, and precision-based production methods. The threshold of 1870 marks the historical break between the First and Second Industrial Revolutions. Industrial methods that had supported rapid economic growth for a century were now insufficient for further expansion. Structural limitations in iron, low efficiency in steam engines, and inadequate precision in machine tools prevented increases in production, urban infrastructure, and global trade capacity. Recorded evidence from technical journals, municipal inspections, industrial correspondence, and factory records establishes that innovation was both necessary and imminent. The documented trajectory of scientific and industrial experimentation directly anticipates the systemic changes that define the Second Industrial Revolution. The large-scale adoption of steel as a construction material, electrification of factories and urban centers, chemical synthesis for industrial and agricultural applications, and precision engineering enabling standardized mass production. The preparatory conditions of 1870 were not gradual or speculative, but observable and quantifiable. Steelmaking experiments using the Bessemer process, patented in 1856 and increasingly applied in the 1860s, provided documented pathways for stronger, more uniform construction materials. Electrical laboratories in Germany, Britain, and the United States were transitioning from experimental dynamos to industrial generators, as evidenced by installation records in Berlin, London, and New York. Chemical laboratories were establishing protocols for controlled synthesis, enabling reproducible production of dyes, pharmaceuticals, and industrial chemicals. Workshops and machine shops were refining milling, grinding, and metal cutting machines to achieve tolerances necessary for complex mechanical systems. Each of these developments was recorded in patents, corporate ledgers, professional journals, and municipal inspections, providing clear historical documentation of industrial change. Industrial pressure in 1870 was systemic rather than localized. Records from the Ruhr Valley, Pennsylvania, and the Lancashire textile districts illustrate simultaneous stress on materials, energy, labor, and transportation networks. Factory reports note production slowdowns due to machinery failure, insufficient rail capacity, and uneven power supply. Municipal inspections report inadequate infrastructure for urban populations. These documented constraints collectively establish 1870 as a moment when the industrial world confronted the limits of previous technological systems and faced empirically determined imperatives for modernization. Steel emerged as the material that would underpin the structural and technological expansion of industrial economies, replacing wrought iron, whose limitations had become apparent in bridges, railways, and machinery. The technical innovations enabling large-scale steel production were already documented in the preceding decade primarily through the development and commercialization of the Bessemer converter patented by Henry Bessemer in 1856 and the Siemens Martin open hearth furnace first applied industrially in the 1860s. Both technologies addressed the critical need for strong, uniform, and cost-effective steel suitable for construction, transportation infrastructure, and machine manufacturing. Production records from Sheffield, the Ruhr Valley, and Pittsburgh show that by the mid-1870s, these furnaces were producing volumes of steel sufficient to meet the rapidly increasing industrial demand, transforming the material basis of the Second Industrial Revolution. The Bessemer process functioned by blowing air through molten pig iron to oxidize impurities, chiefly carbon, silicon, and manganese. Documents from Bessemer Steel Works and technical journals of the period confirm that this process reduced production time and lowered costs compared with puddled wrought iron, while producing steel of uniform tensile strength suitable for load-bearing applications. Between 1870 and 1880, output statistics indicate annual increases in steel production of 15 to 20% in industrial regions of Britain, Germany, and the United States. Company ledgers from Carnegie Steel in Pittsburgh show that by 1875, the firm could produce several 100,000 tons of steel annually, supplying rail lines, bridges, and industrial machinery across the eastern United States. Similar records in the Ruhr Valley document the rapid adoption of the Bessemer and Siemens Martin processes, with firms such as Krupp and Essen demonstrating significant output gains that supported the German industrial expansion. The Siemens Martin open hearth process complemented the Bessemer converter by allowing precise control of the chemical composition of steel. Documents from metallurgical laboratories and production records indicate that open hearth furnaces could produce larger batches with lower risk of structural defects, accommodating more complex applications in bridge building, ship hull construction, and industrial machinery. Engineering surveys from France, Germany, and Britain between 1870 and 1885 provide detailed analyses of the properties of open hearth steel demonstrating superior tensile strength, uniformity, and corrosion resistance compared with wrought iron. These documented advantages facilitated structural projects previously unattainable with iron, including long-span railway bridges, steel-framed buildings, and naval vessels capable of sustaining heavier armaments. The introduction of high-volume steel production directly influenced transportation infrastructure. Railways could now employ steel rails, which were stronger, longer-lasting, and able to sustain heavier locomotives and freight cars than iron rails. Technical reports and maintenance records from the Pennsylvania Railroad, the Midland Railway in England, and the Prussian State Railways document that steel rails required replacement less frequently and allowed higher train speeds, thereby increasing the efficiency of both passenger and freight transport. Bridge inspections and engineering reports from France, the United States, and Germany highlight projects such as the Eads Bridge in St. Louis, completed in 1874 using steel, demonstrating both the structural reliability and economic feasibility of large-scale steel construction. These developments illustrate that steel was not only a material of convenience, but a decisive factor in the operational capacity and expansion of industrial networks. Steel also transformed industrial machinery. Workshops and factory records indicate that machine frames, gears, and shafts fabricated from steel exhibited superior strength and wear resistance compared with iron. Engineers documented that steel machinery could operate at higher speeds and handle greater loads without deformation, increasing output in textile mills, metalworking factories, and locomotive production facilities. Corporate records from Krupp, Siemens, and Baldwin Locomotive Works in Philadelphia detail the integration of steel into machine design, allowing heavier, more precise, and more durable equipment. These improvements were systematically recorded in engineering journals and company reports, providing verifiable evidence of the material's contribution to industrial efficiency. Shipbuilding underwent a similar transformation. Naval and commercial shipyards in Britain, Germany, and the United States adopted steel hulls for large vessels in the 1870s, replacing iron and timber. Technical specifications, procurement records, and engineering schematics from shipyards such as Harland and Wolff in Belfast, A.G. Vulcan in Stettin, and Bethlehem Steel in the United States confirm that steel allowed larger, stronger, and more resilient hulls, accommodating heavier armaments, engines, and cargo. Naval records from Germany and Britain indicate that steel ships supported both commercial expansion and military modernization, creating vessels capable of sustained long-distance navigation and higher load capacity. The documented adoption of steel hulls represents a direct, material transformation of industrial and military infrastructure during this period. Steel production also influenced urban construction. Building permits, architectural plans, and municipal records from Chicago, London, and Berlin demonstrate the emergence of steel-framed buildings, enabling higher structures, wider spans, and increased load-bearing capacity. Architects and engineers recorded the use of steel beams in multi-story factories, warehouses, and office buildings, marking the beginning of what would later be known as skyscraper construction. The documented integration of steel into urban architecture facilitated the densification of industrial and commercial districts, supporting the rapid growth of urban populations documented in census records between 1870 and 1880. Labor and corporate organizations were affected by the steel industry's expansion. Company ledgers, Payroll records and industrial census data show that steel production required a specialized workforce trained in metallurgical techniques, furnace operation, and mechanical handling. German and American steel firms invested in technical schools and apprenticeships to ensure a reliable supply of skilled labor, a documented pattern that underpinned the industry's rapid expansion. Production logs and shipping manifests indicate that steel output supported not only domestic construction and infrastructure, but also international exports, linking industrial centers across Europe, North America, and emerging markets in South America and Asia. International adoption of steel production technologies demonstrates the global significance of the material. Technical journals, patent filings, and correspondence among engineers document the spread of Bessemer and Siemens, Martin furnaces from Britain and Germany to the United States, France, and Austria-Hungary. By 1880, steel production in the Ruhr Valley, Sheffield, and Pittsburgh accounted for a majority of European and North American industrial steel supply. Reports from national statistical bureaus in Britain, Germany, and the United States quantify annual output in millions of tons, reflecting both the technological scalability and economic centrality of steel. Financial records corroborate the industrial and economic impact of steel. Corporate balance sheets and investment reports from the 1870s show that steel enterprises generated substantial profits, reinvested in production facilities, and financed related industries such as railroads, shipyards, and construction companies. Documented capital expenditures in the Ruhr Valley, Pittsburgh, and Sheffield indicate that steel companies expanded furnace capacity, constructed transport infrastructure to supply raw materials, and invested in mechanical workshops, demonstrating the material's centrality to industrial growth. Steel's impact extended to military technology. Warship designs, artillery carriages, and fortifications increasingly relied on steel, as documented in German naval procurement records, British Admiralty reports, and French military engineering studies. High-tensile steel allowed heavier guns, reinforced hulls, and more resilient fortifications. Engineering manuals and testing reports record the specific advantages of steel over wrought iron in resisting impact and stress, providing concrete evidence of its strategic utility. The systematic documentation of steel adoption demonstrates that its integration into industry was neither speculative nor isolated. Company records, engineering surveys, municipal construction reports, technical journals, and government statistics provide verifiable evidence of steel's transformative role. By the late 1870s, steel had established itself as the structural and technological backbone of industrial economies, enabling projects, machines, and infrastructure that were previously unfeasible. Its availability catalyzed the next phase of industrial expansion, including the electrification of factories, the mechanization of production processes, and the reconfiguration of urban and transportation networks. The global steel industry had reached sufficient capacity to transform railway infrastructure and transportation networks, enabling a degree of integration across national and continental scales unprecedented in the prior industrial era. Railroads, previously constrained by wrought iron rails and localized networks, expanded rapidly using steel rails capable of supporting heavier locomotives, longer trains, and higher speeds. Engineering records from the Pennsylvania Railroad, the Midland Railway in England, and the Prussian State Railways provide empirical evidence of the replacement of iron rails with steel beginning in the 1870s. Annual reports indicate reductions in maintenance requirements, higher axle load capacity, and extended operational lifespans for steel rail infrastructure compared with iron. These developments facilitated the movement of bulk goods, raw materials, and passengers across extended distances, directly influencing patterns of industrial growth. Steel rails enabled the construction of transcontinental and interregional lines. In the United States, the Union Pacific and Central Pacific Railroads had completed the first transcontinental railway in 1869, but subsequent decades saw expansion and reinforcement of these lines using steel rails. Corporate records from the Union Pacific show systematic replacement of iron with steel from 1871 onwards, increasing freight tonnage capacity by documented percentages exceeding 20% per decade. Similarly, in Russia, the government directed expansion of the Trans-Siberian Railway, begun in 1891, employed steel rails and bridges, as documented in imperial engineering reports, facilitating connections between European Russia and the Pacific ports. In India, British colonial authorities standardized steel rail installation across the growing rail network, linking interior production centers to port cities such as Bombay, Calcutta, and Madras. These documented expansions demonstrate that steel directly enabled transcontinental connectivity, supporting industrial and commercial integration. Railway expansion was complemented by parallel developments in telecommunication. Telegraph networks, operational since the mid-19th century, were increasingly integrated with rail corridors. Company records, government dispatches, and technical reports show that telegraph lines were systematically installed alongside major railway routes in Europe, North America, and colonial Asia. This integration provided reliable real-time communication between production sites, transport hubs, and commercial centers, enhancing coordination of industrial logistics. For example, the Prussian state railways documented the use of telegraphy for scheduling freight trains and maintaining signaling systems, reducing delays and operational risk. In the United States, telegraph offices at rail junctions enabled immediate communication of shipment arrivals and departures, linking interior manufacturing districts to port facilities. The combination of steel-based rail infrastructure and telegraphic communication created a comprehensive transportation information network capable of sustaining industrial-scale coordination. Urban centers were also directly affected by these infrastructural improvements. Cities in Europe and North America experienced recorded increases in urban population density, coinciding with the expansion of rail networks. Municipal reports and census data indicate that cities such as Chicago, Berlin, Manchester, and Paris relied on rail links to supply food, coal, raw materials, and manufactured goods. Factory production schedules, documented in corporate ledgers, were increasingly tied to railway timetables, reflecting the operational interdependence between industrial centers and transport infrastructure. Rail expansion reduced regional isolation, lowered transportation costs, and allowed industries to concentrate in urban industrial hubs while maintaining access to distant markets and raw material sources. Industrial output itself accelerated in response to enhanced rail capacity. Freight manifests and production records show that coal, iron ore, steel, grain, and manufactured goods moved more efficiently between production centers and ports. For instance, the Ruhr Valley Coal and Steel Complex documented annual increases in coal shipment tonnage from the 1870s onwards, coinciding with upgraded steel rail infrastructure. Similarly, American steel mills in Pittsburgh recorded higher raw material throughput, directly supporting national railway expansion and construction projects. These records establish that the interaction between steel production and railway infrastructure was a mutually reinforcing system, expanding both the capacity and geographical reach of industrial activity. The railroads also supported international trade and integration. Shipping manifests, port authority records, and customs documentation from Hamburg, Liverpool, New York, and Yokohama illustrate that rail transport facilitated the export of industrial products and raw materials. Steel rails, locomotives, machinery, and chemical products were transported to ports for international shipment, while imported coal, iron ore, and cotton reached inland production sites via the same networks. These records demonstrate that railway expansion, enabled by steel, underpinned the growth of global industrial markets, connecting resource extraction, production, and commercial exchange across continents. The United States provides a detailed case of railway-led integration. Corporate and government records show that by 1880, over 90,000 kilometers of track had been laid, much of it utilizing steel rails. Freight statistics document increasing tonnage of coal, iron, timber, and agricultural products transported from interior regions to industrial and urban centers. Engineering surveys indicate that bridges and trestles were constructed from steel to accommodate heavier trains and long spans, reducing maintenance frequency and improving operational reliability. In parallel, telegraph lines were installed along these routes to manage scheduling, train movement, and freight coordination. Together, these developments created an integrated transportation information network that connected interior resources to industrial processing centers and export ports. In Europe, the Ruhr Valley in Germany, northern England, and Belgium experienced similar integration. Corporate ledgers and municipal reports indicate that steel rails replaced iron in both regional and mainline tracks between 1870 and 1885. Freight capacity increased. Industrial centers gained access to coal and raw materials from multiple regions, and urban populations received reliable supplies of goods. Records from the Prussian Ministry of Public Works document the systematic engineering and standardization of rail gauges, signaling, and track construction, emphasizing operational reliability and interoperability across regional networks. Telegraph communication was deployed alongside these rail lines, allowing centralized coordination of industrial logistics, as verified by government and company correspondence. Colonial territories also experienced railway integration during this period. In India, the British administration oversaw the installation of steel rails on key trunk lines connecting production regions with ports. Engineering reports from the Public Works Department indicate that steel enabled higher axle loads, longer train lengths, and reduced track maintenance requirements, all of which contributed to commercial expansion and resource extraction efficiency. Freight records confirm significant movement of agricultural commodities, raw materials, and manufactured goods facilitated by these networks. In Africa, initial railway lines linking mines and ports utilized steel rails by the late 1890s, reflecting the global adoption of the material. The strategic importance of integrated railways was also documented in military and governmental records. European powers, particularly Germany and France, maintained records showing that rail capacity allowed rapid troop and supply movements, a factor noted in strategic planning reports leading up to the 20th century. The deployment of steel rails permitted heavier trains, enabling the movement of artillery, ammunition, and military stores over long distances without structural risk. These records indicate that transportation infrastructure, industrial production, and strategic planning were interdependent, with steel-enabled railways forming the operational backbone. Urban planning and industrial logistics evolved alongside these rail networks. Factory location records, municipal zoning documents, and census data indicate that industrial plants clustered near railway junctions to reduce transportation costs and facilitate the timely delivery of raw materials and finished goods. Ports expanded warehousing and freight handling capacity to accommodate increased throughput. Corporate correspondence shows that coordination between factories, warehouses, and rail terminals was systematically documented, with schedules and timetables adjusted according to production output. This evidence illustrates the direct influence of steel-enabled railway networks on the efficiency and scale of industrial operations. By the 1880s, the combination of steel rails, telegraph integration, and factory connectivity had established a transportation network capable of coordinating production and distribution over vast distances. Freight statistics from Europe and North America demonstrate year-over-year increases in tonnage carried, reductions in transit times, and improvements in operational reliability. Engineering manuals document the use of standardized track gauges, steel bridge construction, and telegraph signaling protocols to ensure safety and efficiency. The coordinated system of transport and communication constituted the documented operational infrastructure supporting industrial expansion and international trade. The adoption of steel-based railways also facilitated technological diffusion. Manufacturers were able to distribute new machinery, chemical products, and electrical equipment more efficiently. Production centers could reach wider markets, and urban populations had greater access to industrially produced goods. Importantly, records confirm that steel infrastructure was both a prerequisite and an enabler for subsequent industrial transformations, including electrification, mechanized production, and chemical manufacturing. Industrial and urban centers confronted increasing limitations in steam-based energy distribution, which had dominated industrial operations since the first industrial revolution. Steam engines, while effective in driving centralized factory machinery, imposed spatial and operational constraints on production facilities. Factory layouts relied on mechanical shafts, belts, and pulleys to transmit power from a single central engine to individual machines, a configuration documented in technical surveys of Lancashire textile mills, Pittsburgh Steel Works, and the Ruhr Valley Metal Works. Maintenance records from these factories report frequent interruptions in production due to shaft misalignment, belt wear, and energy loss, establishing the need for a more flexible and scalable energy source. Concurrently, urban lighting depended largely on gas lamps, which required extensive distribution networks, were prone to leaks, and posed fire hazards. Municipal inspection reports from London, Berlin, Paris, and New York document recurring incidents related to gas lighting infrastructure, including explosions, fires, and irregular illumination. The solution emerged through the application of electrical engineering principles to industrial and urban contexts. Records from Siemens and Halske in Germany, Thomas Edison in the United States, and Werner von Siemens in Prussia show that by the early 1880s, generators capable of producing commercially useful direct and alternating current were operational. Edison's documented development of the 110-volt direct current system, patented in 1880, led to the installation of the Pearl Street Station in New York in 1882, the first documented central electric power station supplying multiple buildings. Company correspondence, patent filings, and operational logs provide evidence of consistent, scheduled delivery of electrical energy to industrial, commercial, and residential customers. The station's operation demonstrated that electricity could reliably replace localized steam engines for small to medium-scale power demands, while enabling distribution over distances sufficient to serve urban districts. European developments occurred in parallel. Siemens and Halske installed arc lighting systems in Berlin by 1882, with municipal approval documented in city engineering reports. Distribution grids using centralized dynamos supplied street lighting, public buildings, and industrial workshops. Technical specifications and municipal inspection reports indicate that early installations powered arc lamps with voltages between 1,000 and 2,000 volts, illuminating streets and public spaces previously limited to gas or oil lamps. Laboratory and installation records from these European systems confirm operational reliability, documenting continuous illumination periods exceeding 8 hours per night and recording energy consumption metrics for performance verification. The expansion of electrical generation was underpinned by improvements in generator and dynamo technology. Technical reports from Werner von Siemens, Elihu Thomson, and Gans and Company describe the application of electromagnetic induction to produce continuous and controllable electric currents at industrial scales. Operational logs from dynamos installed in factories and urban districts show that these machines could deliver hundreds to thousands of kilowatts, enabling both lighting and mechanical applications. Maintenance records indicate that generators were robust and required minimal downtime, providing a consistent power supply critical for industrial productivity. Electrical standards, documented in engineering manuals of the period, were developed to coordinate voltage, current, and distribution parameters, ensuring interoperability and safety across installations. Urban electrification extended beyond lighting. Factory records and municipal documentation from New York, London, and Berlin show that early electrical installations powered small machinery, pumps, and elevators. Textile mills equipped with electric motors reported more uniform illumination and reduced dependency on overhead steam transmission systems. Archival photographs and building schematics from European cities document the integration of electrical wiring into workshop layouts, enabling machinery placement independent of central engine shafts. Correspondence between municipal engineers and factory managers confirms systematic planning of electrical supply to match industrial and public demand, demonstrating the deliberate and documented expansion of electrical infrastructure. The diffusion of electrical networks relied on documented regulatory frameworks. Municipal ordinances in London, 1882, Berlin, 1883, and New York, 1884, specified safety requirements, licensing procedures, and operational standards for power generation and distribution. Inspection reports show that compliance with these regulations reduced incidents of fire and electrical failure and facilitated coordinated integration with existing gas and steam infrastructure. Electrical engineering societies in Germany, Britain, and the United States maintain journals documenting installation practices, generator performance, and system reliability, providing additional sources of empirical evidence for the operational efficacy of early electrification. The use of electricity in transportation infrastructure was simultaneously emerging. Tram systems powered by electricity began operation in Berlin in 1881 and in New York in 1885, as documented in municipal transportation records and corporate logs. These systems employed overhead wires and electric motors to propel passenger vehicles, demonstrating both the flexibility and scalability of electrical power beyond stationary applications. Maintenance records indicate that electrical trams required less labor-intensive operation than horse-drawn alternatives, improved travel speed, and reduced urban congestion. The successful deployment of electric trams provided additional proof of electricity's viability as a core industrial and urban energy source. Power distribution systems were also being documented in industrial contexts. Early factories retrofitted with electrical grids utilized switchboards and circuit breakers, as evidenced by installation manuals from Siemens and Halsk and Edison Electric Light Company. Electrical supply could now be allocated to individual machines, allowing simultaneous operation without mechanical shafting. Factory production logs show measurable increases in efficiency with reduced downtime and improved throughput. Electrical meters installed in workshops recorded consumption rates and enabled managers to optimize power allocation, a practice verified in engineering reports and corporate ledgers. The integration of electrical systems extended to commercial and public lighting, transforming urban environments. Electrical installations were increasingly standardized. Engineering manuals from the late 1880s, including those published by the American Institute of Electrical Engineers and the German Elektrotechnische Zeitschrift, provide detailed instructions for wiring, load distribution, and safety procedures. These manuals documented voltage levels, insulation techniques, grounding methods, and switchgear configurations. Factory and municipal records indicate that adherence to these standards ensured operational consistency, minimized accidents, and facilitated expansion to additional districts or industrial facilities. The documented adoption of electricity during the 1880s laid the foundation for subsequent industrial transformations. Steel factories could now operate electrically powered machinery independent of central steam engines. Urban centers benefited from safer, more reliable lighting systems. Transportation infrastructure incorporated electric trams and signaling equipment. Laboratory and industrial experiments demonstrated that electricity could provide sufficient power density and distribution reliability for both mechanical and lighting applications. Archival correspondence from Siemens and Halsk, Edison Electric Light Company, and municipal engineering offices confirms the systematic documentation, experimentation, and deployment of electrical systems, establishing an empirical basis for widespread adoption. The impact of early electrification extended to industrial scheduling and production planning. Factory records show that electric lighting allowed extended working hours with consistent illumination. Machine operation logs indicate that electrically powered tools maintained steady performance throughout shifts, reducing downtime caused by variable steam pressure or mechanical failure. Engineering evaluations measured efficiency gains, quantifying output increases attributable to electrical power. These documented improvements in industrial productivity provided an empirical rationale for further investment in electrical infrastructure, both in factories and urban centers. By the close of the 1880s, records from Europe and North America demonstrate that electrification had transitioned from laboratory experimentation to operational infrastructure capable of supporting large-scale industrial and urban needs. Factory ledgers, municipal inspection reports, engineering surveys, and patent filings collectively verify the deployment of central power stations, distribution networks, electric lighting, and small-scale mechanical applications. The introduction of electricity into urban and industrial centers catalyzed a fundamental reorganization of factory operations. Steam power had dictated a centralized layout. A primary engine drove line shafts, which transmitted mechanical energy via belts and pulleys to individual machines. Engineering surveys from Lancashire textile mills, Ruhr Valley steel workshops, and American iron foundries documented the limitations of these systems, highlighting frequent mechanical failures, uneven power distribution, and constrained factory design. Electrical motors replaced this model, allowing distributed power, independent operation of machinery, and more adaptable production spaces. Installation records from Siemens and Halsk, General Electric, and German manufacturing archives detail the systematic deployment of electric motors across diverse industries, including textiles, metalworking, and machinery assembly. Electric motors were applied in multiple configurations. Direct drive motors could power single machines, while centralized electric generators fed a network of motors distributed throughout the factory floor. Maintenance logs from workshops in Pittsburgh and Sheffield show that individual motors reduced downtime caused by mechanical transmission failures and allowed rapid reconfiguration of production lines. Factories could now operate machines simultaneously at varying speeds, improving efficiency and enabling the simultaneous processing of different production stages. Technical manuals from the period describe the implementation of motor-driven lathes, planers, presses, and textile machinery, noting measurable increases in output and precision. Factory layout underwent systematic restructuring. Historical blueprints and engineering reports illustrate a transition from narrow, linear arrangements dictated by line shafts to open floor plans with flexible machine placement. Overhead power distribution systems, documented in installation schematics from General Electric and Siemens, allowed motors to be positioned independently of a central drive shaft. This spatial flexibility facilitated access for operators, reduced mechanical interference, and improved safety. Records indicate that production floors could expand or contract in response to demand, a capability not achievable under centralized steam power. Electrification enabled higher operational speeds. Machinery performance logs and corporate production records demonstrate that electric motors maintained consistent rotational speeds and torque, reducing variations that previously affected quality and output. In textile production, electric spinning frames and looms operated at higher speeds without compromising thread integrity. Steel and metalworking facilities documented the use of motorized rolling mills, hammers, and grinders, showing reductions in processing time per unit. Factory ledgers from 1885 to 1895 record corresponding increases in output, with industrial firms noting measurable improvements in efficiency and production volume attributable directly to electric power. Energy management was enhanced through empirical documentation. Electrical meters, maintained in workshops and factories, recorded power consumption for individual motors. Logs from factories in Chicago, Berlin, and Manchester show systematic monitoring of electrical usage, enabling managers to adjust load distribution and optimize machine operation. Engineering analyses, published in period journals, demonstrated that distributed electric power reduced energy loss associated with long mechanical transmission lines, providing a quantifiable improvement over steam-based layouts. Textile mills exemplify the documented advantages of electrification. Records from Lancashire mills indicate that the installation of electric motors allowed individual control of spinning frames and weaving machines, enabling variable speeds and independent operation. Production logs confirm reductions in thread breakage, improved fabric uniformity, and increased output per worker. Correspondence between mill engineers and company management describes the retrofitting process, including rewiring floors, installing switchboards, and training operators in the use of electric motors. These documents provide verifiable evidence of systematic industrial adoption of electrification and the resulting productivity gains. Metalworking industries similarly benefited. Reports from Krupp in Essen, Baldwin Locomotive Works in Philadelphia, and Vickers in Sheffield document the installation of electric rolling mills, grinders, and lathes. These machines, powered by individual motors, allowed precision work on steel and iron components, including shafts, gears, and machine parts. Technical journals and factory correspondence note the improvement in tolerances, reduction of scrap material, and faster production cycles. Documented improvements in component uniformity facilitated assembly processes and prepared industrial systems for subsequent mass production methods. Labor organization within electrified factories changed in documented ways. Payroll records and factory logs show that electric motors reduced the reliance on specialized operators required to manage line shafts, belts, and steam engines. Workers could now focus on machine operation and maintenance rather than continuous mechanical adjustment. Safety records indicate a reduction in accidents associated with moving belts and pulleys, while maintenance logs confirm decreased downtime from mechanical failure. These documented changes reflect operational improvements rather than speculative analysis of worker behavior. Industrial safety and infrastructure reliability were enhanced. Factory inspection reports and municipal safety records from New York, Berlin, and Manchester document reductions in fire risk as reliance on steam-driven line shafts and open belts declined. Wiring diagrams and engineering notes show systematic implementation of circuit breakers, fuses, and insulated cabling, ensuring controlled power distribution. Technical evaluations published in professional journals quantified the performance of these systems, recording failure rates, maintenance requirements, and operational efficiency. These empirical measures demonstrate that electrification provided documented, verifiable improvements to industrial reliability and workplace safety. The integration of electric power facilitated expansion in factory size. Factory blueprints and municipal construction permits indicate that electrified facilities could occupy larger floor areas without requiring additional centralized steam engines. Overhead power distribution and strategically placed motors allowed a consistent energy supply across expanded production halls. Archival correspondence from industrial engineers describes a systematic evaluation of floor load capacities, motor placement, and electrical wiring to optimize both energy use and spatial configuration. These records confirm that factory design adapted empirically to the technical advantages of electric power rather than to speculative assumptions about industrial needs. Documentation also shows that electrification enabled incremental technological improvement. Technical journals from the 1880s and 1890s report experiments with different motor designs, voltage distribution schemes, and control mechanisms. Laboratories within Siemens, General Electric, and German chemical firms maintained empirical records of motor performance, recording torque, rotational speed, energy consumption, and mechanical wear. Factory logs show that these empirical evaluations informed upgrades and standardization of machinery, creating a continuous cycle of technical improvement. These developments laid the foundation for precision engineering and the eventual implementation of assembly line production in multiple sectors. Power reliability extended beyond individual factories. Municipal electrical networks, documented in Berlin, Paris, London, and New York, provided a consistent energy supply for industrial, commercial, and public lighting applications. Engineering reports detail redundancy in generation and distribution systems, ensuring uninterrupted operation for critical industrial processes. Maintenance logs and operational correspondence indicate scheduled inspection and repair protocols, providing verifiable evidence of operational reliability. Industrial firms documented contingency plans, including backup generators and network interconnections, reflecting systematic management of energy supply. The documented transformation of industrial operations included significant cost efficiencies. Corporate financial records show reductions in maintenance expenses for machinery previously driven by line shafts, decreased material losses due to improved precision, and increased output per worker. Comparative analyses between steam-driven and electrically powered workshops provide quantitative evidence of efficiency gains, measured in production throughput, energy consumption, and labor allocation. These records demonstrate that electrification produced measurable, verifiable improvements in both economic and operational terms. Electrified factories also enabled experimentation with novel production methods. Archival correspondence from chemical and mechanical firms documents the installation of variable speed motors to adjust processing parameters, optimize chemical reactions, and improve product quality. Empirical data from these experiments informed engineering standards and process control methods, which were systematically published in industrial journals. These documented innovations provided the foundation for further technological advances, including automated and semi-automated production processes in the early 20th century. Integration of electrical systems into industrial operations facilitated coordination with transportation infrastructure. Factory dispatch records, railway manifests, and port logs indicate that consistent electrical operation enabled reliable scheduling for production and shipment of goods. Electrified machinery allowed factories to maintain production rates in alignment with transport timetables, reducing bottlenecks and improving the flow of materials between industrial centers and distribution points. These operational improvements are substantiated by empirical data in corporate and municipal archives. By the close of the 1890s, documentation confirms that electrification had fundamentally altered factory operations across multiple industrial sectors. Factory blueprints, technical manuals, maintenance logs, corporate correspondence, municipal inspection reports, and engineering journal articles collectively provide empirical evidence of the transition from centralized steam-driven layouts to distributed electrical motor systems. Industrial expansion and the reorganization of factories under electrification created both demand and capacity for systematic chemical production. Existing chemical practices, derived from artisanal methods and early industrial chemistry, were inadequate to meet the scale, precision, and variety of requirements in textiles, pharmaceuticals, and agriculture. Documentation from German firms, particularly BASF, Bayer, and Hoechst, illustrates the establishment of laboratory-based, large-scale chemical operations during the 1880s and 1890s. patent filings, corporate ledgers, and laboratory notebooks confirm the systematic transition from batch to continuous chemical processes. Controlled reactions, precise temperature and pressure regulation, and analytical verification became standard methods in production, marking a clear departure from pre-industrial chemical practices. Synthetic dyes were among the first widely documented products of this industrial chemical transformation. Records show that BASF and Hoechst scaled the production of synthetic aniline and alizarin dyes, previously synthesized in laboratory conditions but now manufactured in ton-scale quantities. Production logs, quality control reports, and patent documentation detail the chemical pathways and operational parameters for these compounds. Textile mills across Germany, Britain, and France received shipments of standardized synthetic dyes, as recorded in shipping manifests and commercial invoices. These dyes allowed industrial textile operations to produce fabrics with consistent color and fastness, facilitating the mass production of clothing, upholstery, and industrial textiles. Pharmaceutical production also transitioned to systematic, industrial methods. Bayer's documented production of salicylic acid and later acetylsalicylic acid demonstrates the integration of chemical synthesis with industrial-scale quality control. Laboratory notebooks and production records show empirical testing of purity, reaction yields, and storage stability, ensuring that medicinal compounds met reproducible standards. Records indicate that the move from small-scale laboratory synthesis to factory-scale production required the construction of specialized reactors, automated feeding systems, and controlled crystallization processes. Distribution ledgers and pharmacy inventories confirm the circulation of these products across Europe and North America, demonstrating a fully operational industrial pharmaceutical system. Agriculture benefited directly from chemical industrialization through the production of synthetic fertilizers. Corporate archives from BASF and German chemical research institutes document large-scale synthesis of ammonium nitrate, superphosphate, and potassium compounds. Agricultural extension reports, governmental agricultural statistics, and export records indicate that these fertilizers increased crop yields in Germany, France, and the United States. Technical manuals published by chemical firms describe reaction optimization, production line monitoring, and storage protocols for large-scale fertilizer operations, providing documented evidence of systematic scientific methods applied to agronomic needs. These developments transformed food production capabilities and provided the raw material foundation for industrialized urban populations. The chemical revolution also influenced construction and heavy industry. Records show that chemical compounds such as synthetic sulfuric acid, hydrochloric acid, and alkalis were produced in industrial quantities, supporting metal processing, textile bleaching, and paper production. Engineering reports and factory production logs detail the integration of these chemicals into industrial workflows. The scale of chemical production enabled multiple sectors to expand simultaneously, creating a documented correlation between chemical availability and industrial throughput. Industrial laboratories became essential to the chemical sector. Documents from Bayer, Hoechst, and BASF confirm the systematic employment of chemists within corporate laboratories, where empirical studies guided process optimization, product development, and quality control. Laboratory notebooks reveal stepwise experimentation with reaction conditions, catalysts, and purification methods. Production records indicate that findings were implemented directly into factory operations, producing standardized outputs with reduced variability. Patent documentation corroborates the systematic development of chemical processes, providing legally and technically verifiable evidence of innovation and scale-up. Scientific methods drove reproducibility and efficiency. Measurement protocols, titration data, and spectroscopic analyses were recorded in company laboratories and verified across multiple production sites. Production logs show controlled scaling of reactions, monitoring of temperature, pressure, and concentration, and documented yields for each batch. Archival correspondence between laboratories and factories confirms the continuous feedback loop between experimentation and industrial application, providing empirical justification for process modifications and product scaling. Chemical synthesis supported the expansion of other industrial sectors. Synthetic dyes enabled high-volume textile production in mills already electrified, as detailed in factory shipping logs and procurement records. Fertilizers increased agricultural outputs, supplying urban populations and factory workforces with consistent food supplies, as verified by governmental agricultural surveys. Chemical intermediates, including acids and solvents, facilitated precision metalworking, paper production, and photographic processes. Documentation from technical journals and factory records confirms that industrial chemistry functioned as a cross-sectoral enabling technology, integral to multiple strands of Second Industrial Revolution development. Corporate strategies integrated scientific research and production. Management records from BASF, Bayer, and Hoechst illustrate the alignment of laboratory experimentation with production capacity planning, raw material acquisition, and distribution logistics. Stock inventories, shipping logs, and purchase orders document systematic scaling and standardization of chemical products. Correspondence and internal reports provide direct evidence that decisions on process implementation were based on measured chemical and production data rather than anecdotal observation or speculative reasoning. Quality control and standardization became embedded in chemical industry practices. Production logs show regular sampling, analysis, and validation of chemical products before distribution. Shipping records note concentrations, purities, and batch numbers, establishing traceability from laboratory synthesis to industrial application. Engineering and chemistry journals of the period describe procedures for process monitoring, including pH measurement, temperature regulation, and reaction duration control. Documentation indicates that such standards were codified within companies, producing reproducible, high-quality outputs essential for industrial, agricultural, and pharmaceutical markets. International dissemination of chemical technologies is empirically documented. Export manifests from German chemical firms show shipments of dyes, fertilizers, and pharmaceuticals to Britain, France, the United States, and colonial markets in India and Africa. Technical manuals and translated patent filings circulated in multiple countries, providing documented guidance for production replication. Laboratory training programs and industrial apprenticeships ensured that the technical expertise required for chemical manufacturing was transmitted systematically, as recorded in personnel files and company training logs. The chemical revolution also accelerated environmental and logistical systems within industry. Factory water treatment records, documented in BASF and Hoechst archives, show controlled handling of reaction byproducts, such as spent acids and alkalis, to prevent interference with production and mitigate hazards. Transportation logs indicate the use of specialized containers and railcars for chemicals, ensuring safe and efficient delivery to industrial and agricultural users. These operational records demonstrate the integration of chemical manufacturing into wider industrial logistics networks, reinforcing empirical coordination across sectors. By the close of the 19th century, the chemical industry had established a comprehensive operational and technological foundation. Patent filings, laboratory notebooks, corporate ledgers, municipal records, and shipping manifests collectively provide documented evidence that chemical production had moved from artisanal or experimental scales to systematic, industrialized processes. Synthetic dyes, pharmaceuticals, fertilizers, and industrial chemicals were produced, distributed, and applied with measurable consistency, verified by laboratory analysis and industrial inspection. The systematic development of chemical, electrical, and mechanical industries necessitated organized research beyond traditional workshop experimentation. Industrial firms confronted complex technical problems, including process optimization, material development, and production scalability. Documentation from Siemens, General Electric, BASF, Bayer, and Hooks shows that corporations established dedicated laboratories to institutionalize innovation, moving beyond isolated chemists or engineers working ad hoc. Corporate records, laboratory notebooks, patent filings, and correspondence confirm that these facilities operated as formal centers for research, staffed with trained chemists, physicists, and engineers. The structure of these laboratories integrated empirical scientific methods into industrial operations. Technical logs and experimental notebooks detail systematic approaches to testing chemical reactions, electrical generation, motor performance, and metallurgical properties. Laboratories implemented standard procedures, including controlled variables, repeated trials, and detailed measurement documentation. Production records indicate that results from laboratory experimentation were directly applied to scaling industrial processes, as shown in steel rolling, chemical synthesis, and electrical machinery production. Engineering journals of the period report that these laboratories enabled consistent improvements, reducing variability in output and enhancing product quality. Corporate R&D departments developed formal hierarchies and specialized divisions. Siemens archives show departments focused separately on electrical generation, telecommunications, and electromechanical devices. BASF and Bayer documents describe divisions for synthetic dyes, pharmaceuticals, and fertilizers, with dedicated research chemists, laboratory technicians, and process engineers. Memoranda and internal reports indicate that research objectives were aligned with corporate production goals, including yield optimization, cost reduction, and process reliability. Company correspondence demonstrates that laboratory findings were translated into production specifications, machine designs, and standardized operational procedures. The integration of laboratories into industrial operations produced measurable improvements across multiple sectors. In chemical industries, BASF records show optimization of ammonia synthesis, dye production, and acid purification, directly increasing output volumes while maintaining consistent quality. Electrical laboratories at Siemens and General Electric conducted tests on dynamos, motors, and distribution systems, documenting voltage regulation, efficiency gains, and load performance. Metallurgical laboratories in German and American steel firms evaluated alloy compositions, rolling temperatures, and forging techniques, resulting in stronger, more reliable steel for bridges, rails, and machinery components. Documentation from factory logs, laboratory notebooks, and corporate reports establishes a continuous feedback loop between experimental research and industrial application. Patent filings from this period provide empirical evidence of research-driven innovation. Siemens registered patents for alternating current motors and telegraphy equipment, General Electric for incandescent lighting and dynamos, and BASF for chemical processes such as synthetic alizarin production. Patent applications include detailed schematics, empirical measurements, and procedural descriptions. These filings were cross-referenced in corporate laboratories to ensure reproducibility and to guide process improvements. Archival correspondence and laboratory records show that patented inventions were integrated into production with documented performance metrics, demonstrating a direct link between formal R&D and industrial output. The rise of industrial laboratories coincided with the development of standard analytical techniques. Laboratories utilized titration, spectroscopy, calorimetry, and metallography to quantify chemical composition, electrical efficiency, and material properties. Laboratory manuals, technical reports, and academic publications provide empirical data on test procedures, calibration methods, and measurement standards. Production records from corresponding factories confirm that results obtained in laboratories were implemented to control reaction conditions, motor performance, and alloy consistency. This systemized approach eliminated reliance on artisanal judgment or trial-and-error practices, creating repeatable, measurable outcomes. Corporate R&D facilitated innovation in process control and automation. Siemens and General Electric documented methods for regulating generator output, distributing electrical loads, and synchronizing motors in large-scale industrial installations. In chemical firms, BASF and Bayer logs detail the monitoring of reaction temperatures, pressures, and feedstock concentrations to maintain consistent production quality. These practices were documented empirically, with laboratory notebooks recording variables, observations, and outcomes. Integration into industrial operations allowed companies to scale production with minimal variation and predictable performance. Human capital management became a component of R&D strategy. Personnel records show recruitment of specialized chemists, engineers, and technicians trained in university laboratories or previous industrial positions. Siemens and General Electric archives record structured training programs, apprenticeships, and rotations between laboratory and factory settings to ensure practical application of experimental findings. Documented coordination between laboratory personnel and production engineers facilitated the translation of theoretical insights into operational processes. Correspondence and internal reports verify that professional expertise was systematically harnessed to maximize technical efficiency. Documentation indicates that industrial laboratories drove both incremental and radical innovation. In chemical industries, empirical records describe process improvements, including enhanced yields in dye production and acid purification. Electrical laboratories conducted systematic testing of insulation materials, conductor design, and dynamo configurations, leading to higher efficiency and lower operational failure rates. Metallurgical laboratories analyzed steel and alloy microstructures, informing improvements in rolling, casting, and forging techniques. Corporate reports indicate that laboratory-directed innovations were consistently implemented, monitored, and refined across multiple production facilities. Industrial laboratories also provided predictive insights for future applications. Siemens engineers documented testing of alternating current distribution systems, including voltage regulation and load balancing, anticipating citywide electrification. BASF chemists conducted controlled experimentation with chemical precursors, evaluating stability, reactivity, and process scalability, allowing foresight in product development. Laboratory notebooks from these firms include empirical measurements and calculations predicting production capacities, safety requirements, and operational efficiencies, demonstrating systematic planning grounded in documented observation rather than conjecture. R&D departments enhanced inter-firm knowledge transfer. Internal memoranda, correspondence with universities, and published technical reports facilitated the dissemination of empirical findings. Journals such as Elektrotechnische Zeitschrift and Zeitschrift für Chemie und Industrie regularly documented laboratory procedures, experimental results, and performance benchmarks. These publications created a documented basis for replication and verification, ensuring that empirical methods and technological improvements extended beyond a single firm. Corporate archives show that information exchange improved efficiency, reduced duplication of errors, and promoted standardization of industrial practices. Financial records indicate that corporate investment in R&D yielded measurable returns. BASF and Bayer accounting ledgers show correlations between laboratory-derived process improvements and increases in production output, reductions in raw material waste, and lower operational costs. Siemens and General Electric records indicate similar effects in electrical machinery production, including reliability gains and energy efficiency improvements. These documented metrics demonstrate the empirical efficacy of organized research in directly supporting industrial growth. The institutionalization of R&D also influenced strategic industrial planning. Laboratories were tasked with long-term problem solving, such as developing higher-capacity electrical generators, synthesizing novel chemical compounds, and producing stronger alloys. Documentation in company strategy reports details planned laboratory experiments, projected production outcomes, and anticipated market applications. Empirical data collected from laboratory trials informed corporate decision-making regarding factory expansion, capital investment, and workforce allocation. Archives show that laboratory findings were systematically integrated into operational and strategic planning, providing verifiable evidence of their central role in industrial advancement. By the turn of the century, industrial laboratories had become permanent and essential features of corporate organization. Records from Siemens, General Electric, BASF, Bayer, and Hooks demonstrate that these laboratories produced continuous improvements in electricity, chemistry, and materials science, forming a structured, empirically grounded basis for industrial progress. Laboratory notebooks, patent filings, production logs, corporate correspondence, and technical publications collectively confirm that the research conducted within these institutions was systematically translated into industrial applications, standardizing innovation, improving efficiency, and ensuring reproducible results. The development and industrial application of internal combustion engines marked a decisive technological advance within the Second Industrial Revolution, building directly on empirical knowledge from industrial laboratories and precision engineering. Engineers across Germany, France, and the United States implemented systematic experiments to develop engines fueled by gasoline, kerosene, or heavy oil. Patents, technical reports, laboratory notebooks, and company records document the iterative design, testing, and scaling of these engines. Firms such as Benz and C. Daimler Motorengesellschaft, Maybach, and Rudolf Diesel's laboratory established methodical approaches to engine thermodynamics, fuel injection, combustion efficiency, and mechanical reliability, with measurements recorded under controlled conditions. The early internal combustion engines were designed to surpass the limitations of steam engines in power-to-weight ratios, responsiveness, and operational flexibility. Laboratory tests conducted by Daimler and Maybach detail small, high-speed gasoline engines capable of powering mobile vehicles rather than stationary machinery. Correspondence between engineers and production managers describes precise cylinder dimensions, fuel-air mixture ratios, ignition timing, and cooling mechanisms. Empirical data from engine trials included torque measurements, revolutions per minute, fuel consumption, and operating temperatures, forming a structured, verifiable basis for subsequent production models. Benz's company archives document the transition from experimental engines to fully constructed motor vehicles. The Benz patent motor wagon, produced in 1885 and 1886, incorporated a single-cylinder four-stroke engine, chain drive, and a rudimentary clutch system. Technical schematics, patent documentation, and factory assembly logs confirm systematic testing of engine components, chassis design, and drivetrain performance. Production records indicate that initial vehicles were produced in limited quantities for demonstration and sale, with incremental improvements informed by empirical observations recorded in engineering notebooks. Parallel developments occurred in Daimler Motorengesellschaft, where engineers focused on high-speed, lightweight engines suitable for both road vehicles and stationary machinery. Laboratory experiments included heat management, carburation efficiency, and mechanical lubrication, documented in technical reports and engineering correspondence. Maybach's contributions to engine design, including compact, high-revving motors, were recorded in production specifications and test reports. These primary sources confirm that early automotive engineering relied on empirical, repeatable experimentation rather than speculative design. Diesel engines represent a complementary branch of internal combustion development. Rudolf Diesel's laboratory notebooks detail thermodynamic calculations for high-compression engines operating on heavy oils, with attention to efficiency, pressure containment, and mechanical durability. Patents filed by Diesel in the 1890s provide stepwise schematics of engine design, including cylinder arrangement, fuel injection timing, and cooling systems. Factory logs and technical correspondence confirm small-scale production of engines for industrial applications, including ships, generators, and stationary machinery, before their adaptation for transportation purposes. Empirical data indicates significant improvements in fuel efficiency and sustained power output compared with steam engines of equivalent capacity. The scaling of internal combustion engines relied on industrial precision and standardized parts. Factory records from Benz and Daimler show detailed machining tolerances, crankshaft alignment specifications, and cylinder bore measurements, all verified through repeated inspection and documented in quality control ledgers. These processes allowed consistent assembly of multiple engines, ensuring interchangeability of components, which was essential for industrial-scale vehicle production. Technical publications of the period detail metallurgical analyses, indicating the use of high-strength steel alloys for cylinders, crankshafts, and connecting rods, confirming verifiable improvements in durability and operational reliability. Transportation and commercial infrastructure adapted to support internal combustion engines. patent filings, municipal permits, and road construction records show systematic improvements in road surfaces, fueling stations, and logistical networks to accommodate motorized vehicles. Engine performance reports include documented range, fuel consumption, and maintenance requirements, providing empirical guidance for deployment of vehicles in commercial, industrial, and passenger contexts. Correspondence between vehicle manufacturers and city planners, documented in municipal archives, demonstrates coordinated integration of early motorized transport with urban infrastructure. Production of internal combustion engines also intersected with electrification and the chemical industries. Electrical systems powered ignition mechanisms, lighting, and instrumentation, documented in technical manuals from Benz and Daimler. Lubricants, fuels, and cooling agents produced by chemical firms were specified in production and laboratory records, showing precise formulations for engine operation and longevity. Corporate correspondence confirms empirical testing of chemical inputs for compatibility with mechanical components, ensuring that production outputs adhere to standardized performance criteria. Industrial adoption of engines expanded rapidly in multiple sectors. Archival records document the use of gasoline engines in small vehicles, industrial machinery, and riverboats, with detailed logs of operational performance and maintenance schedules. Early buses, trucks, and agricultural machinery utilized engine designs derived directly from Benz, Daimler, and Diesel's empirical trials. Factory ledgers confirm production volumes, delivery dates, and component quality, establishing a traceable record of industrial application rather than anecdotal or speculative usage. The early automotive industry produced incremental but continuous improvements. Production notes, laboratory tests, and patents document iterative enhancements in carburetor design, ignition systems, and cooling mechanisms. Cylinder materials, piston rings, and engine housings were empirically tested under varying operational conditions, with results recorded in engineering notebooks. These improvements were systematically implemented across subsequent production runs, forming a documented chain of innovation leading to higher efficiency, reliability, and commercial viability. By the 1890s, internal combustion engines entered commercial markets in Europe and the United States. Factory records from Benz, Daimler, Peugeot, and Oldsmobile show initial production runs, sales invoices, and documented service records. Technical journals verify operational performance, fuel efficiency, and engine longevity. Vehicle specifications, including engine displacement, horsepower, and fuel capacity, were standardized and recorded in patent filings and corporate ledgers, ensuring empirical consistency across manufactured units. Documentation confirms the integration of internal combustion engines into industrial operations beyond transportation. Factory installation records from Germany, Britain, and the United States show engines powering pumps, compressors, and auxiliary machinery. Maritime applications are evidenced by shipbuilder logs, indicating the installation of diesel engines for propulsion and power generation. These applications demonstrate the versatility of internal combustion technology and its systematic adoption across industrial sectors, substantiated by verifiable documentation rather than anecdotal accounts. Internal combustion engines also influenced urban mobility and commercial logistics. Municipal permits, transportation logs, and sales records show the operation of engine-powered buses, delivery vehicles, and trucks in cities such as Berlin, Paris, London, and Chicago. Empirical data on vehicle range, operational hours and maintenance requirements were recorded by operators and manufacturers, allowing incremental improvements in design, fueling practices, and urban deployment strategies. These documented adaptations show systematic integration of engine technology into industrial and urban infrastructure. By the early 20th century, documented evidence indicates that internal combustion engines had become a core component of industrial modernization. Corporate archives, technical journals, patent filings, factory records, and municipal transportation logs collectively confirm that engines powered a broad array of vehicles and machinery, providing mobility, efficiency, and flexibility unavailable with steam-based systems. Standardization of parts, empirical testing of performance, and integration with chemical and electrical inputs ensured reproducibility, durability, and scalability across multiple industrial sectors. The proliferation of internal combustion engines, complex machinery, and industrial electrical systems highlighted the need for precise, reproducible mechanical components. Industrial firms responded by developing machine tools capable of producing standardized parts with consistent tolerances. Factory logs, engineering manuals, patent filings, and technical reports from the late 19th and early 20th centuries document systematic methods for achieving mechanical uniformity across production runs. Companies such as Brown and Sharp, Singer Manufacturing, Pratt and Whitney, and German firms including Siemens and Krupp led the development of these precision engineering systems, establishing empirically verifiable benchmarks for industrial quality and reproducibility. Machine tools evolved to meet industrial demands. Milling machines, lathes, planers, and grinders were designed with precise guides, calibrated scales, and adjustable components to maintain tight tolerances. Engineering journals, factory manuals, and patent records detail specifications, including allowable deviations in millimeters or fractions thereof for critical components. Documented testing procedures included repeated measurements, gauge verification, and controlled environmental conditions to ensure that components produced at separate factories remained interchangeable. Archives from Brown and Sharp reveal extensive calibration records and inspection logs demonstrating the routine application of empirical standards. Standardized parts facilitated the assembly of complex machinery, including internal combustion engines, electrical generators, textile looms, and industrial pumps. Production records show that cylinder bores, pistons, shafts, gears, and valves were manufactured to exacting dimensions, ensuring interchangeability and minimizing assembly errors. Correspondence between engineers and factory foremen confirms that early automotive engines, electric motors, and textile machinery relied on standardized components to maintain operational consistency. Technical schematics preserved in patent archives document both component dimensions and assembly sequences, providing verifiable evidence of systematic standardization. Interchangeability of parts enabled scale in manufacturing. Factory records indicate that identical components produced at multiple locations could be assembled without adjustment. Archival documentation from Singer Manufacturing shows standardized sewing machine parts produced in separate workshops assembled seamlessly in final production. Similarly, Siemens documented production of electric motors with interchangeable armatures and commutators, ensuring consistent electrical performance. Industrial correspondence confirms that this standardization reduced assembly time, improved reliability, and facilitated maintenance, providing empirical validation of the advantages of precision engineering. The development of precision tools also intersected with metallurgical advances. Steel alloys produced through Bessemer, open hearth, and later electric furnace processes provided uniformity and mechanical strength necessary for precise machining. Metallurgical analyses, laboratory records, and production logs demonstrate consistent material properties, such as hardness, tensile strength, and thermal expansion, which were essential for maintaining dimensional tolerances. Industrial laboratories systematically tested batches of steel and other metals, providing empirical data for machine tool calibration and part design. Inspection systems became integral to precision manufacturing. Factory archives, particularly from Pratt & Whitney and Krupp, describe methods including gauge blocks, micrometers, vernier calipers, and optical comparators to verify part dimensions. Records indicate routine sampling of parts, with documented measurements compared against prescribed tolerances. Deviations were recorded and corrective actions implemented, establishing a documented quality assurance process. Technical publications detail these inspection protocols, confirming that standardized measurement and verification were applied consistently across multiple industrial sectors. The adoption of standardized parts enabled more complex mechanical assemblies. Internal combustion engines, for example, required pistons, valves, and crankshafts machined to precise dimensions to maintain efficiency and durability. Production logs from Benz, Daimler, and Peugeot confirm repeated testing of individual components for weight, shape, and surface finish, ensuring compatibility and performance. Engineering correspondence demonstrates systematic verification of tolerances and assembly outcomes, providing empirically documented evidence of precision manufacturing processes. Precision engineering also supported electrification and electrical machinery. Siemens and General Electric archives document armatures, commutators, and motor housings machined to standardized specifications. Laboratory tests measured rotational balance, electrical conductivity, and mechanical wear. Factory logs record repeated inspections and corrective measures for components deviating from established specifications. Technical publications in electrotechnical journals document methods for producing uniform conductors, insulation, and magnetic cores, demonstrating empirically controlled engineering practices. Mass production and interchangeable parts were linked empirically through precision engineering. Factory records show sequential assembly methods where standardized components were fitted without modification. Documents from Singer Manufacturing illustrate assembly line practices facilitated by precision machine parts, allowing operators to construct complete sewing machines rapidly and consistently. In automotive production, archives from Ford Motor Company demonstrate the preconditions of mass assembly, machine parts with minimal variance, verified through repeated measurement, ensuring functional assembly without adjustment. Industrial machine tools themselves were improved through empirical study. Technical manuals, patent applications, and laboratory reports document enhancements in spindle speed, cutting depth, feed rates, and vibration control, directly informed by testing and operational data. Documentation from Brown and Sharp details iterative improvements in milling machines, grinding machines, and lathes based on measurements of surface finish, dimensional accuracy, and throughput. Production and laboratory records confirm the feedback loop between operational experience and machine tool refinement, creating a continuous improvement cycle grounded in empirical observation. The influence of standardized parts extended to maintenance and repair. Factory manuals, correspondence, and field service records demonstrate that replacement components could be installed without modification, reducing downtime and labor costs. Technical specifications, part catalogs, and instruction manuals provide empirically verified dimensions and assembly procedures. Archival evidence from Krupp, Siemens, and American machine shops indicates a systematic recording of part numbers, dimensions, and material grades, enabling reproducible maintenance and long-term operational reliability. Precision engineering also facilitated new mechanical innovations. Gear systems, camshafts, and valve mechanisms in engines and machinery were designed with calculable tolerances, empirically tested through repeated measurement and load analysis. Laboratory notebooks and factory records confirm that these designs underwent iterative refinement, with recorded performance data guiding modifications. Technical documentation demonstrates the empirical basis for innovations such as high-speed engines, multi-stage electrical generators, and automated textile machinery, establishing a chain of verifiable engineering progress. Documentation shows that standardized parts supported industrial scalability beyond a single factory. Correspondence between company branches, shipping records, and assembly manuals indicates that components manufactured in separate locations could be transported, assembled, and operated with consistent performance. This distributed manufacturing capability, verified in corporate records, allowed rapid expansion of production capacity and contributed to regional and national industrial growth. Empirical documentation confirms that precision engineering and standardization underpinned this scalable industrial model. By 1910, empirical records show that precision engineering and standardized parts formed the technical foundation for mass production systems. Factory logs, inspection reports, engineering notebooks, and corporate correspondence collectively verify that systematic measurement, material control, and component interchangeability enabled complex machinery and engines to be produced at scale. Standardized parts became integral to automotive, textile, electrical, and chemical machinery, providing a reproducible, empirically documented basis for industrial efficiency and technological advancement. The widespread adoption of standardized parts and precision engineering created the technical conditions necessary for mass production, enabling industrial firms to assemble complex products at unprecedented scale and speed. Factory records, technical manuals, patent filings, and corporate correspondence indicate that mass production systems were initially implemented in various sectors, including firearms, sewing machines, and machine tools. Companies such as Singer Manufacturing, Remington, and Colt documented assembly practices that relied on interchangeable components and workflow standardization, allowing multiple operators to construct complete products simultaneously with predictable outcomes. Documentation shows that the transition from craft-based assembly to mechanized, sequential production required the coordination of multiple specialized workstations. Factory logs and operational blueprints from Singer Manufacturing describe sequential assembly lines in which each worker performed a defined set of operations repeatedly. Detailed time-motion studies, recorded in company archives, analyzed task durations, component placement, and assembly sequences. Empirical evidence demonstrates that these methods reduced variability, improved efficiency, and increased output without compromising quality. The automotive industry was the first to implement large-scale moving assembly techniques, with Ford Motor Company providing the most systematically documented example. Factory ledgers, engineering blueprints, An internal correspondence confirmed that Ford adopted a conveyor-based moving assembly line in 1913 at the Highland Park plant. The process relied on standardized components produced with tight tolerances, empirically verified through repeated measurements and inspections. Components, including engine blocks, axles, and transmission elements, were delivered to the line in pre-measured, verified form, eliminating the need for individual adjustments during assembly. Empirical documentation demonstrates the impact of moving assembly line techniques on production metrics. Ford production reports indicate that the assembly time for a Model T automobile was reduced from over 12 hours to approximately 93 minutes per vehicle after the line was implemented. Factory logs record worker task durations, component arrival schedules, and defect rates, providing detailed verification of time and efficiency gains. Correspondence between production managers and engineers confirms that standardized parts, precision tools, and workflow coordination were critical to achieving these outcomes. Assembly line implementation required rigorous coordination of component supply, factory layout, and labor allocation. Ford corporate archives detail scheduling methods, including pre-positioned parts, synchronized supply carts, and defined task sequences. Time studies, engineering notebooks, and production reports demonstrate empirically measured task durations, load balancing, and throughput optimization. These records indicate that operational efficiency was systematically monitored and adjusted based on quantitative data, creating a controlled industrial environment that minimized downtime and bottlenecks. Documentation from contemporaneous industrial journals shows that other firms studied Ford's methods and implemented partial assembly line techniques. Reports from German automotive manufacturers, including Daimler and Opel, describe the use of moving subassemblies and mechanized conveyors to increase production volume. British and American industrial journals provide empirical data on time savings, component standardization, and defect reduction achieved through sequential assembly techniques. These records confirm that assembly line principles were empirically validated and replicated across multiple industrial contexts. The integration of mass production required complementary improvements in materials, tools, and processes. Steel for chassis, engines, and structural components was produced in standardized forms and tested for mechanical consistency. Factory logs indicate that rolling mills, forging shops, and machine tool operations supplied parts that met predefined dimensional tolerances, verified through repeated measurement. Lubricants, fuels, and electrical systems were controlled and specified for reliability. Documentation confirms that the combination of precision engineering, material standardization, and sequential assembly was empirically responsible for the reproducibility and efficiency of mass-produced goods. Labor management practices were formalized to support mass production. Time motion studies, recorded in corporate archives and industrial manuals, established task allocation, work pacing, and break schedules. Reports indicate that empirical observation of worker performance informed adjustments to workstation layout and process flow. Employee training manuals preserved in factory records described standardized operational procedures, ensuring consistent assembly practices. These empirical management methods complemented technical standardization, producing predictable output and minimizing assembly errors. Empirical documentation also shows that mass production reduced manufacturing costs. Ford accounting ledgers indicate reductions in labor hours per unit, material waste, and overhead allocation, supported by time studies, inventory records, and cost analyses. Production reports compare pre-assembly line output to post-assembly line performance, quantifying efficiency gains. Correspondence between engineers and financial managers demonstrates that the assembly line, coupled with standardized parts, delivered measurable cost savings, enabling broader market distribution and lower consumer prices. Mass production also influenced quality control systems. Factory inspection logs from Ford and Singer Manufacturing show multi-stage verification processes for critical components and final products. Standardized measurement tools, such as micrometers, gauges, and calipers, were employed at each stage of assembly to ensure compliance with specifications. Engineering reports indicate that defect rates decreased as assembly procedures became more standardized, demonstrating empirically that mass production enhanced product reliability in addition to efficiency. The integration of mass production in the automotive sector created a feedback loop for continuous improvement. Internal reports, engineering notes, and patent applications document iterative enhancements in assembly line speed, component layout, and workflow sequencing. For example, conveyor speeds were adjusted based on observed worker performance and component handling times, verified through repeated measurements. Process innovations, such as pre-assembled subunits and modular chassis components, were systematically tested, documented, and implemented to further improve throughput. Documentation shows that mass production principles spread beyond automotive manufacturing. Textile factories adopted mechanized sequential assembly for looms and finishing equipment, while electrical machinery firms implemented conveyor-based subassembly procedures for dynamos and motors. Factory records, technical manuals, and trade journals detail empirical methods of adapting assembly line concepts to diverse industrial contexts, confirming that mass production became a reproducible, cross-sector manufacturing methodology. Corporate archives indicate that mass production also enabled strategic industrial expansion. Inventory records, production forecasts, and factory construction plans document increased capacity, consistent output, and predictable scheduling, facilitating market growth. Empirical analysis of production logs confirms that firms could reliably plan shipments, allocate labor, and coordinate supply chains over extended periods. These records demonstrate that mass production provided verifiable operational stability at an industrial scale, directly supporting economic expansion during the Second Industrial Revolution. Empirical evidence demonstrates the broader economic and industrial impact of mass production. Corporate reports, census data, and trade statistics document rapid increases in automobile, machinery, and consumer goods output in the United States and Europe. Factory logs indicate that assembly line implementation allowed production volumes to increase several-fold while maintaining quality standards. Technical publications corroborate these findings, providing data on throughput, labor efficiency, and unit cost reduction, all empirically validated through operational records. Mass production influenced ancillary industrial processes as well. Steel mills, chemical plants, and machine tool manufacturers increased output to supply assembly line operations. Documentation confirms that precision-engineered components, standardized materials, and controlled process conditions were essential to sustain high-volume assembly operations. Internal correspondence and technical reports indicate that suppliers coordinated production schedules, quality control, and logistics based on empirically documented requirements from assembly line manufacturers. By 1913, Empirical documentation shows that the moving assembly line at Ford's South Highland Park plant represented a culmination of earlier Second Industrial Revolution innovations, including standardized parts, precision engineering, empirical workflow analysis, and coordinated material supply. Factory logs, production reports, patent filings, and corporate correspondence provide verifiable evidence of systematic reductions in assembly time, improvements in reliability, and increased output. These records confirm that mass production was both technologically and organizationally grounded, representing a quantitatively measured advance in industrial efficiency. The rapid expansion of industrial production, particularly following the implementation of mass production techniques, generated profound transformations in urban environments and labor structures. Archival population records, municipal reports, and census data document significant increases in the size and density of industrial cities across Europe, the United States, and Japan. Cities such as Berlin, Manchester, Chicago, Paris, Vienna, and Osaka experienced population growth rates ranging from 2% to 5% annually, driven by the migration of workers from rural areas and smaller towns to urban industrial centers. Municipal archives record the development of new housing districts, transportation infrastructure, sanitation systems, and water supply networks to accommodate these expanding populations. Industrial employment records confirm that factories became central employers in urban economies. Corporate ledgers from steel mills, automotive plants, textile factories, and chemical works indicate substantial workforce expansions, including men, women, and increasingly adolescent laborers. Employment registers detail working hours ranging from 10 to 12 hours per day, 6 days per week, with variations depending on regional labor laws and industry type. Wage records provide documented evidence of remuneration differences by skill level, occupation, and geographic location, allowing for quantitative analysis of labor distribution. Concurrently, the concentration of workers in urban industrial centers prompted the formation of organized labor structures. Union records, meeting minutes, and correspondence from trade organizations such as the American Federation of Labor, the British Trades Union Congress, and the German Allgemeiner Deutscher Gewerkschaftsbund provide documented evidence of membership growth, strike activity, and negotiation strategies. Industrial disputes, including documented strikes in the Ruhr coal fields, the textile districts of Lancashire, and the steelworks of Pittsburgh, illustrate systematic attempts by workers to improve wages, working conditions, and hours. Records from these events include strike declarations, arbitration outcomes, and employer correspondence, providing verifiable accounts of labor activism. Legislative records document responses to industrial labor pressures. In Britain, parliamentary records from the Factory Acts, late 19th and early 20th centuries, codified maximum working hours for women and children, prescribed safety standards, and mandated workplace inspections. In the United States, state factory laws and labor commissions compiled reports on working conditions, accident rates, and compliance with labor statutes. German imperial archives document industrial regulations and social welfare programs, including accident insurance and old age pensions, implemented in the 1880s and 1890s to stabilize labor relations. These measures were recorded in legal statutes, governmental correspondence, and administrative reports, establishing verifiable evidence of systemic labor reform. Urban infrastructure development was a direct response to industrial population growth. Municipal engineering records, city planning documents, and water and sanitation reports describe the expansion of street networks, sewer systems, bridges, and public transportation. Gas, electric, and water utilities maintain logs detailing installation schedules, consumption records, and service coverage, providing empirical documentation of urban modernization. Public health records, including morbidity and mortality statistics, reflect the impact of industrial living conditions on urban populations, informing documented reforms such as improved waste management, clean water provision, and housing regulations. Housing records confirm the emergence of industrial working-class districts characterized by high density, limited space, and variable sanitary conditions. Land registries, construction permits, and property surveys document the development of tenements, row houses, and multifamily dwellings. Building inspection records indicate structural deficiencies, occupancy limits, and compliance with emerging housing codes, forming empirical evidence for the correlation between industrial employment and urban habitation patterns. Housing committees and municipal correspondence document efforts to improve worker living conditions through planned housing developments and regulated construction standards. Education and vocational training are also adapted to industrial urban environments. School registers, technical institute curricula, and apprenticeship records provide evidence that industrial centers promoted specialized education for laborers and technicians. Technical schools in Germany, Britain, and the United States documented the systematic instruction of skills in mechanical engineering, electrical work, chemical production, and metallurgical processes. Apprenticeship contracts and examination records confirm structured pathways for skill development, ensuring a consistent supply of trained labor to sustain industrial growth. Industrialization and urban concentration also affected transportation and logistics within cities. Municipal traffic reports, tramway records, and railway timetables document the expansion of intra-urban transport networks to facilitate commuting for large workforces. Corporate records from factories detail worker arrival schedules, employer-provided transport arrangements, and coordination with municipal authorities. These logistical adaptations were empirically monitored, recorded, and adjusted based on observed usage and efficiency, demonstrating systematic planning in response to urban industrialization. The concentration of labor and the growth of urban industrial society created new economic and social pressures. Statistical analyses in governmental reports, corporate correspondence, and trade journals document occupational health hazards, industrial accidents, and mortality rates in factory environments. Accident registers, workers' compensation records, and medical reports quantify injury rates, providing an empirical basis for safety regulations and labor reform initiatives. Industrial engineering studies included time and motion analyses, risk assessments, and recommendations for mechanized safeguards, forming a documented foundation for occupational health standards. Industrial employment also affected social stratification within urban environments. Census data, wage records, and occupational surveys provide empirical evidence of hierarchical labor divisions, distinguishing between skilled engineers, machine operators, clerical staff, and unskilled laborers. Housing records and city directories indicate residential segregation along occupational and economic lines, with managerial and technical personnel often residing in suburban or newly developed urban districts. These documented distributions illustrate the structural organization of labor within industrial societies. Labor organization industrial disputes, and legislative responses are documented in extensive governmental and corporate records. Arbitration reports, strike resolutions, and union communications confirm systematic negotiation between workers and employers, providing empirical evidence of social adaptation to industrial pressures. Industrial accident reports and employer insurance records quantify workplace risks, informing statutory interventions. These records collectively illustrate the structured response to social change induced by industrialization, rather than relying on anecdotal narratives or interpretive assumptions. Urban municipal governance also adapted to industrial concentration. City council minutes, public works budgets, and urban planning reports detail systematic investments in sanitation, transportation, education, and housing. Empirical evaluation of infrastructure projects, including traffic flow studies, sewer system performance, and housing occupancy surveys, guided resource allocation and urban planning decisions. Archival evidence shows that these measures were coordinated with industrial production schedules, workforce needs, and municipal regulatory frameworks, demonstrating documented integration of industrial growth and urban management. Public health initiatives, documented in hospital records, municipal health reports, and epidemiological surveys, targeted diseases exacerbated by dense industrial living conditions. Sanitation reforms, vaccination campaigns, and inspection regimes were implemented in response to empirically recorded morbidity and mortality data. Industrial companies contributed to these efforts through health programs, documented in corporate correspondence, providing workers with access to medical care and preventive measures. These interventions are documented as empirically informed responses to industrial urbanization. Industrial urbanization also influenced cultural and recreational infrastructure. Municipal budgets, library records, and park development plans document investments in theaters, sports facilities, public libraries, and cultural institutions aimed at improving worker welfare. Attendance records, subscription ledgers, and program schedules provide verifiable evidence of engagement with these facilities, reflecting a systematic integration of social infrastructure within industrial urban environments. Overall, the period demonstrates empirically documented social adaptation to industrial expansion. Census data, municipal planning documents, labor union records, and corporate archives collectively establish the link between mass production, urbanization, labor organization, and public infrastructure development. Industrial societies systematically responded to population growth, workforce concentration, and technological change through documented measures, including housing regulation, labor reform, public health initiatives, education, and municipal services. The expansion of industrial production, standardized manufacturing, and mass production systems established a foundation for significant shifts in global economic and political power. Economic data, trade records, and governmental reports from the late 19th and early 20th centuries document the rising industrial capacities of the United States, Germany, and Japan relative to the previously dominant British industrial base. Industrial output statistics, corporate production ledgers, and metallurgical reports provide quantifiable evidence of comparative manufacturing growth across nations. Germany emerged as a leading industrial power, surpassing Britain in several key sectors by the early 20th century. Statistical data from the Prussian Statistical Office and corporate archives indicate rapid growth in the steel, chemical, and electrical industries. The German steel output increased significantly through the adoption of the Bessemer process and Siemens-Martin furnaces, with production concentrated in the Ruhr region. Company records from Krupp and Thyssen demonstrate large-scale manufacture of railway components, naval guns, and industrial machinery, reflecting both domestic demand and export capacity. Archival correspondence confirms systematic coordination between industrial firms and government ministries to optimize production and technological advancement. Germany's chemical industry provides further documented evidence of industrial ascendance. Archival production reports from BASF, Bayer, and Hoechst detail laboratory-based synthesis of dyes, pharmaceuticals, and fertilizers. Empirical records show systematic improvements in chemical production processes, quality control, and product standardization. Exports of chemical products expanded significantly between 1880 and 1914, as documented in customs records and trade reports, indicating the country's integration into global industrial markets. Government reports demonstrate that German industrial strategy supported research and infrastructure investment, facilitating long-term competitiveness. The United States experienced rapid industrial growth, fueled by expansion in steel, railways, machinery, and electrical manufacturing. Census data, corporate production ledgers, and engineering journals document output increases and regional industrial concentration. Pittsburgh Steelworks and Bethlehem Steel Archives record increasing output volumes and the implementation of standardized production methods. Railroads, including the Pennsylvania Railroad and New York Central, expanded with steel rails, verified through engineering reports and operational logs. Industrial journals document innovations in assembly line practices, time motion studies, and material handling techniques, highlighting empirically measured efficiency gains. The U.S. chemical sector, though initially less advanced than Germany's, expanded rapidly with the establishment of synthetic dye plants, fertilizer production, and industrial chemical facilities. Corporate records from chemical firms indicate the adoption of laboratory-based production methods, closely monitored for consistency and reproducibility. Government reports on industrial patents, exports, and trade balance provide evidence of the United States integrating chemical production into its broader industrial expansion. Electrical manufacturing, notably through General Electric and Westinghouse, further enhanced American industrial competitiveness, with production logs, technical manuals, and patent filings documenting systematic innovation and capacity growth. Japan, following the Meiji Restoration, initiated a state-directed industrialization program. Government archives, factory construction records, and educational reports document the importation of Western technologies and the establishment of domestic manufacturing capacity. Industrial facilities in Osaka, Tokyo, and Nagoya produce textiles, steel, and machinery under monitored processes based on empirical engineering methods. Census records, factory ledgers, and customs data confirm increasing output, while trade records indicate that Japan became integrated into regional and global markets, demonstrating measurable industrial growth in a compressed time frame. Britain, although historically dominant, experienced a relative decline in comparative industrial performance. Statistical reports from the Board of Trade and Engineering journals document slower growth in steel, electrical, and chemical sectors relative to Germany and the United States. Production ledgers, patent filings, and corporate correspondence indicate continued innovation in textiles and shipbuilding but a relative stagnation in new industrial sectors. Government reports document concerns over labor productivity, capital investment, and industrial efficiency, corroborating a measurable shift in global industrial balance. Industrial competition was also evidenced by quantitative measures of output in steel, coal, and electrical equipment. Annual production statistics from national bureaus, company reports, and engineering societies document that Germany and the United States overtook Britain in steel production by the early 20th century. Coal output, essential for energy-intensive industries, followed similar trends, with Ruhr coal fields, Pennsylvania anthracite mines, and Japanese collieries expanding operations. Production data show correlations between resource extraction, industrial capacity, and technological innovation, providing empirical evidence of strategic industrial advantage. Technological dissemination further contributed to global competition. Patent records, engineering publications, and technical correspondence document cross-national exchange of industrial knowledge, including machinery designs, chemical synthesis methods, and electrical systems. German, American, and British engineers maintained empirically documented trials and replication of production methods, providing verifiable records of comparative industrial capability. Technical societies, trade journals, and international exhibitions further facilitated observation, measurement, and benchmarking of industrial innovations across nations. International trade and finance amplified industrial competition. Customs reports, shipping manifests, and trade balance documents indicate increased exchange of industrial goods, raw materials, and finished products. German steel and chemicals, American machinery, and British textiles circulated in global markets, with recorded tariffs, import-export volumes, and shipping logs providing empirical confirmation of competitive positioning. Financial records, including bank reports and corporate investment statements, document capital flows supporting industrial expansion, infrastructure development, and technological implementation. Naval construction and armament production illustrate the strategic dimension of industrial competition. German naval archives, British Admiralty reports, and U.S. Navy records quantify the number of steel-hulled vessels, artillery systems, and ordnance output. Shipbuilding logs document the integration of standardized steel components, mechanized production, and precision engineering. Industrial capacity for armaments directly correlated with national strategic planning, as verified through government procurement reports and corporate production records, demonstrating empirically measured power shifts based on industrial capability. Railway networks also reflected industrial competition. National railway boards and corporate records indicate expansion and modernization using standardized steel rails, mechanized signaling systems, and telegraph coordination. Comparative statistics show that Germany and the United States constructed more extensive and higher capacity networks than Britain, providing empirically verifiable metrics for logistical and industrial efficiency. Correspondence between railway engineers and government ministries confirms systematic coordination to optimize transportation for industrial supply chains. Labor force development contributed to national industrial capacity. Census data, employment registers, and vocational training records indicate that Germany, the United States, and Japan invested in technical education, apprenticeships, and professional training. Documented outcomes include the production of skilled engineers, machinists, and technicians capable of sustaining large-scale industrial operations. Factory training logs and apprenticeship contracts provide empirical evidence for systematic workforce development aligned with industrial competitiveness. State policy intersected with industrial capacity. Government archives from Germany, the United States, and Japan document legal frameworks supporting industrial expansion, including tariffs, subsidies, research funding, and infrastructure investment. Ministry correspondence, legislative acts, and technical reports confirm state involvement in directing resources, monitoring output, and coordinating strategic industrial development. Empirical data from these sources demonstrate a measurable influence of industrial policy on national competitive positioning. Scientific and technical research underpinned industrial performance. Corporate laboratory notebooks, patent filings, and industrial research reports indicate systematic experimentation in chemical synthesis, metallurgical processes, electrical systems, and mechanical engineering. Empirically documented results facilitated innovations that provided competitive advantages, including improved steel alloys, synthetic dyes, and precision components. Cross-national exchange of technical literature further amplified industrial efficiency, as documented in professional journals and conference proceedings. By 1914, the global industrial landscape had shifted markedly. Comparative production data, national statistics, and corporate records confirm that Germany and the United States surpassed Britain in several strategic sectors, while Japan emerged as a significant regional industrial power. Industrial competition drove both technological advancement and geopolitical positioning, with empirical evidence from production, trade, and policy documents illustrating verifiable shifts in global power structures. Industrial capacity became a central factor in national policy, military preparedness, and international economic strategy. The culmination of technological and industrial development by the early 20th century directly shaped national military and strategic capabilities, as documented in government archives, military correspondence, corporate production records, and engineering journals. Industrial innovations in steel production, electrical machinery, chemical synthesis, precision engineering, and internal combustion engines provided a foundation for mechanized infrastructure, modern armaments, and rapid mobilization. Production ledgers, patent filings, and operational reports confirm that industrial capacity increasingly defined national power, without recourse to anecdotal or interpretive accounts. Steel output records from Germany, Britain, and the United States demonstrate significant increases in both volume and quality. The Ruhr, Sheffield, and Pittsburgh archives detail large-scale production of structural steel, high-grade rails, naval hull plates, and artillery-grade steel. Empirical data from metallurgical reports indicate improvements in alloy composition, casting techniques, and heat treatment, enabling the construction of heavier, more resilient structures. Shipyard logs from Kiel, Portsmouth, and New York document the fabrication of steel-hulled warships, confirming the direct application of industrial steel capacity to naval modernization programs. Railways, built with these high-strength steel components, served both commercial and strategic functions. National railway records indicate extensive networks optimized for freight capacity and rapid troop movement. Engineering blueprints and telegraph installation logs show that the integration of electrical signaling and communication along rail lines enabled coordinated logistics over continental distances. Records from the Prussian State Railway and the Pennsylvania Railroad demonstrate empirical evidence of capacity, reliability, and synchronization, providing quantifiable support for the strategic utilization of industrial transport infrastructure. Advances in chemical production, documented in corporate archives from BASF, Bayer, and Hoechst, contributed directly to military preparedness. Production ledgers record the manufacture of synthetic dyes, fertilizers, explosives, and pharmaceuticals. Explosive production, including nitroglycerin and picric acid, is verifiably documented through factory output reports, safety logs, and government inspection records, demonstrating that chemical industry expansion had measurable implications for armament supply. Pharmaceutical production, including analgesics, antiseptics, and disinfectants, is similarly documented in corporate and medical archives, indicating direct support for military and civilian health systems. The development of electrical machinery, motors, and power generation systems enabled mechanized operations in factories and military production facilities. Engineering notebooks, technical manuals, and factory logs from Siemens, General Electric, and AEG confirm the installation of high-capacity dynamos, power distribution networks, and electrically driven machinery. Production records illustrate increased efficiency, reliability, and flexibility, ensuring that industrial infrastructure can sustain both civilian and military manufacturing demands. Electrical engineering advances also extended to naval applications, with shipboard generators and electrically operated weaponry documented in naval procurement reports. Internal combustion engines, developed by Benz, Daimler, Maybach, and Diesel, provided increased mobility and mechanical versatility. Factory production ledgers and patent records document the design, testing, and manufacture of engines with higher power-to-weight ratios than steam engines. Industrial records indicate that these engines powered early automobiles, trucks, marine vessels, and stationary industrial machinery, providing empirically verified improvements in mobility and operational flexibility. Military correspondence documents engine adaptation for vehicles, artillery transport, and light marine craft, evidencing direct application to strategic capabilities. Precision engineering and standardized parts supported complex industrial and military systems. Machine tool company records, including those from Brown and Sharp and German Maskinen Fabrik, document capabilities for producing components within tightly controlled tolerances. Logs of milling, grinding, and threading operations confirm repeatability and dimensional accuracy essential for engines, artillery, naval machinery, and industrial equipment. Assembly records verify that standardized parts facilitated rapid repair, component interchange, and operational continuity, providing a documented basis for the industrial underpinning of military readiness. Armament production increasingly relied on industrial precision and scale. Krupp, Vickers, and Bethlehem Steel records detail the large-scale manufacture of artillery, small arms, and naval ordnance. Production logs include material input, fabrication processes, heat treatment schedules, and inspection records, providing empirically measured evidence of capacity, quality, and efficiency. Factory correspondence with military departments documents delivery schedules, compliance with technical specifications, and production targets, confirming that industrial systems were systematically aligned with strategic needs. Naval modernization reflects the intersection of steel, precision engineering, and mechanization. Shipyard logs from Germany, Britain, and the United States detail the construction of dreadnoughts and armored cruisers, with steel hull plating, high-powered engines, and electrically operated weaponry. Engineering plans and procurement records provide quantitative evidence of displacement, armor thickness, engine output, and armament configuration. Production schedules verify coordination between steel mills, engineering workshops, and shipyards, demonstrating that industrial systems enabled scalable and reproducible military capacity. Communication technology augmented industrial and military coordination. Telegraph and telephone network records, including installation logs and operational manuals, document systematic coverage of industrial and strategic zones. Wireless telegraphy, documented in naval and army reports, allowed real-time communication for fleet coordination and command infrastructure. These networks were systematically integrated with transportation, factory, and military logistics systems, verified through installation records, operational tests, and maintenance logs. Industrial capacity thus encompassed not only production, but also the communication infrastructure essential for strategic deployment. Industrial research laboratories continued to enhance technology. Corporate and government records from Siemens, General Electric, Krupp, and the German Imperial Naval Office document systematic experimentation in metallurgy, chemical synthesis, electrical systems, and mechanical engineering. Laboratory notebooks, patent applications, and test reports verify empirical methods, reproducibility, and documented innovation. These laboratories ensured a continuous flow of technical improvements, directly supporting industrial efficiency and military applications. Urban industrial infrastructure also played a strategic role. Municipal records, factory blueprints, and transportation logs document the concentration of production facilities near railways, ports, and electrical grids. Water supply and sanitation records show planning to maintain workforce health and operational continuity. Empirical documentation of workforce allocation, factory output, and material flow demonstrates a methodical integration of urban industrial capacity with national strategic requirements. By the early 1910s, industrial capacity had become a measurable factor in national security calculations. Ministry reports, military planning documents, and economic statistics quantify output in steel, chemicals, machinery, and energy. Comparative data indicate that Germany, the United States, and Britain had developed sufficient industrial infrastructure to support large-scale mobilization. Government and corporate records confirm coordination between production, research, logistics, and military deployment planning, evidencing systematic preparation for potential conflict. Empirical observation of industrial growth, technological integration, and strategic application demonstrates that the Second Industrial Revolution established the structural conditions for mechanized modern warfare. Production capacity, material standardization, transportation networks, and communication systems created a documented framework for rapid military mobilization. Archival evidence from military procurement, industrial output logs, and research laboratories confirms that technological and industrial systems were optimized for both economic and strategic functions. Technological interdependence also became apparent. Engineering reports, production schedules, and factory correspondence illustrate that advances in one sector, such as steel production, directly influenced capabilities in others, including naval construction, railway expansion, and artillery manufacturing. Chemical industry output supported both agricultural productivity and explosives manufacturing. Electrical generation enabled mechanized factories, signaling systems, and transport infrastructure. Internal combustion engines provided mobile power for vehicles, vessels, and industrial operations. Documentation confirms that the integrated industrial base was empirically measured, interconnected, and systematically exploited for strategic purposes. By 1914, industrial innovation, capacity, and organization had reached a structural peak. Factory ledgers, corporate correspondence, and governmental statistics document maximum output in steel, chemicals, electrical machinery, engines, and armaments. Engineering reports and naval construction logs verify the operational readiness of industrial systems. Research laboratories continued to supply incremental technological improvements. Taken together, these records confirm that industrial systems created during the Second Industrial Revolution formed the foundation of national power, logistical coordination, and military preparedness in the years immediately preceding the First World War. The outbreak of the First World War in 1914 marked the abrupt transformation of industrial systems developed over 4 decades into instruments of modern warfare. Archival government records, factory production logs, and military procurement documents confirm that steel, chemical, electrical, and mechanical production shifted almost immediately from civilian to military application. Empirical evidence demonstrates that industrial capacity, labor organization, and technological infrastructure established during the Second Industrial Revolution directly determined the pace, scale, and effectiveness of wartime mobilization. Steel production, which had underpinned railways, urban construction, and industrial machinery, became the primary material for armaments, armored vehicles, and naval vessels. Production ledgers from the Krupp Works in Essen, Bethlehem Steel in Pennsylvania, and Vickers in the United Kingdom document the immediate reallocation of steel output to artillery, naval hull plates, machine guns, and ammunition. Reports indicate increases in furnace operation time, expanded blast furnace output, and rapid standardization of steel alloys to meet military specifications. Shipyard records confirm accelerated construction schedules for dreadnoughts and cruisers, utilizing prefabricated steel sections produced in civilian industrial networks. Railways facilitated strategic mobilization. National railway authorities, including the Deutsche Reichsbahn, British Railway Boards, and the U.S. Army Transport Service, maintained operational logs recording troop movements, material transport, and timetables for ordnance delivery. Electrical signaling systems, telegraph networks, and station scheduling records demonstrate documented coordination across civilian and military sectors. The existing industrial railway infrastructure allowed for unprecedented logistical throughput, with empirically measured capacity ensuring rapid deployment to border regions and ports. Chemical industries, initially focused on dyes, fertilizers, and pharmaceuticals, redirected output to explosives, propellants, and medical supplies. Production reports from BASF, Bayer, and Hoechst record increases in nitric acid, ammonium nitrate, and picric acid output. Factory inspection logs verify adherence to safety and quality standards necessary for munitions production. Pharmaceutical production, including antiseptics and analgesics, continued to support both military and civilian health services, as documented in hospital records and Army Medical Corps inventories. Chemical plants expanded operating hours and implemented empirical process improvements to maximize wartime throughput. Internal combustion engines, developed over previous decades for vehicles and industrial machinery, were adapted for military use. Factory production ledgers from Daimler Motorengesellschaft and Benz indicate reconfiguration of engines for trucks, armored vehicles, and naval craft. Operational logs and engineering blueprints confirm modifications for durability, fuel efficiency, and battlefield performance. Shipyard documentation shows internal combustion engines installed in torpedo boats and auxiliary vessels, providing quantifiable improvements in mobility and logistical flexibility. Electrical systems were extended to wartime production, communications, and weaponry. Factory installation records, municipal electric utility logs, and military correspondence detail the use of high-capacity dynamos and distributed electric power for munitions factories, armament assembly, and field depots. Telegraph and telephone systems, combined with electrical signaling, allowed empirically verified synchronization of production schedules and supply chains. Records of electrical inspections, maintenance logs, and power output confirm operational reliability under increased wartime demand. Precision engineering and standardized parts became essential to maintaining large-scale production. Company records from Brown and Sharp, Krupp, and Bethlehem Steel detail the manufacture of interchangeable components for artillery, firearms, vehicles, and naval machinery. Inspection logs, quality control reports, and production schedules confirm empirically measured tolerances, enabling rapid assembly, replacement, and repair of military equipment. Military procurement documents corroborate the utilization of pre-standardized parts to maintain operational continuity in field conditions. Armament production reached levels unprecedented in civilian industrial history. Krupp and Vickers output logs document artillery shells, rifles, machine guns, and heavy ordnance produced in quantities verified by factory ledgers and shipment records. Bethlehem Steel records detail the production of naval guns, ammunition, and structural components for military installations. Correspondence with military departments confirms delivery schedules, adherence to technical specifications, and rapid scaling of production to meet frontline demand. Empirical measurement of output demonstrates the decisive role of industrial infrastructure in war preparedness. Naval construction, drawing on steel, electrical, and mechanical innovations, expanded rapidly. Shipyard archives in Kiel, Portsmouth, and New York document the launch of dreadnoughts, cruisers, and auxiliary vessels using prefabricated steel sections, high-output engines, and standardized armaments. Engineering drawings, displacement measurements, and armament records confirm design specifications and operational readiness. Production schedules and dockyard logs provide empirical evidence of accelerated shipbuilding enabled by industrial coordination and prior technological investment. Labor allocation adapted immediately to wartime priorities. Employment records, factory logs, and government labor directives confirm the mobilization of male and female labor forces, including the reallocation of skilled workers to munitions and heavy industry. Factory schedules document extended shifts, segmented labor rotations, and reorganization of tasks to maximize output efficiency. Governmental labor reports verify compliance with wartime production requirements, workforce distribution, and documentation of occupational hazards. Industrial research laboratories continued to innovate under wartime conditions. Corporate laboratory notebooks, patent filings, and experimental reports from Krupp, Siemens, and General Electric document process improvements, new explosive formulations, chemical stabilizers, and mechanical enhancements. Laboratory correspondence and technical memoranda demonstrate the empirical testing of materials, machinery, and chemical compounds under operational conditions. These innovations supported increased industrial throughput, equipment reliability, and strategic application in the war effort. Transportation and logistics systems integrated civilian and military industrial outputs. Railway timetables, telegraph logs, and factory shipment records document systematic coordination to move raw materials, semi-finished goods, and finished armaments. Warehousing ledgers, port authority logs, and military supply inventories provide quantitative evidence of throughput, storage capacity, and distribution efficiency. Engineering assessments of infrastructure capacity confirm empirically measured performance under increased operational loads, ensuring strategic support for frontline operations. Urban industrial infrastructure continued to support both civilian needs and wartime production. Municipal archives, factory blueprints, and public utility records document adaptations to water supply, sanitation, electrical distribution, and transportation to maintain operational continuity. Health inspection reports, hospital records, and workforce accommodation logs demonstrate empirically verified measures to protect workforce productivity, mitigate industrial hazards, and sustain production levels. By the end of 1914, the industrial networks constructed between 1870 and 1914 were fully mobilized for warfare. Production statistics, military inventories, corporate reports, and government correspondence confirm the large-scale reorientation of industrial capacity. Steel, chemicals, engines, electricity, and precision machinery were systematically applied to armaments, logistics, and strategic infrastructure. Documented output, coordination mechanisms, and technological integration provide empirical evidence that the Second Industrial Revolution's industrial mechanisms directly enabled sustained, mechanized modern warfare. The mobilization demonstrates that industrialization not only transformed economic structures, but also fundamentally altered the execution of conflict. Empirical production records, engineering logs, and military correspondence provide measurable proof that civilian industrial systems became central instruments of military power. The systematic allocation of steel, chemical production, electrical infrastructure, internal combustion engines, and precision machinery underlines the inseparability of industrial capability and wartime operational effectiveness.